Today I will present two families of model Riemannian manifolds, the spheres and the hyperbolic spaces. So given R positive, S and R denotes the sphere of radius R centered at the origin of Rn plus 1. Endow it with the metric denoted by this symbol, and which is called the round metric of radius R. Which is induced from the Euclidean metric on Rn plus 1. It is possible to prove that the isometry group of SNR is ON plus 1. That is the group of orthogonal matrices of n plus 1 times n plus 1 orthogonal matrices. It's possible to prove that ON plus 1 acts transitively on O SN R. Do you remember what OSNR means? This means the disjoint union of all orthonormal of the set of all orthonormal bases of T, P, S, and R. And if we use the language introduced last time, this says that SNR is a frame homogeneous. How to prove this result? Suppose that P is a point of S and R, and B B1, B2, Bn is an orthonormal basis of TPSNR. We will show that there exists linear map represented by an element of On plus 1. So there exists an orthogonal map that sends the North Pole N to P and the basis, the orthonormal basis of Tn Sn R to B1 Bn. It's enough to prove only this, because if you have another point of the sphere and the corresponding orthonormal basis of the tangent space to the sphere at that point, to prove that there exists an orthogonal map which sends P to this new point and this basis to the new orthonormal basis, you just compose the inverse of this map with the map that you get using the construction I will show you now, and replacing P by the new point. So in other terms, if alpha sends N to P and alpha dot B1 Bn, sorry, delta 1 delta n equal B1 B2 Bn, and beta is the map that you can construct in the same way as we will do for alpha, but which sends N to Q and this orthonormal basis to this orthonormal basis, so orthonormal basis of T, Q, S, and R. Then if you want an orthogonal map which sends P to Q and this basis to this basis, just consider the composition of alpha inverse and beta. So it remains to understand how to construct alpha. So if P belongs to SNR, then the length of P is R, implies P hat equal to P over R, has length 1, and it points in the same direction as P. So since B1, B2, Bn, this is a basis of P, P, S, and R, then Bi is orthogonal to P hat, and this implies that B1, Bn, P hat, this is an orthonormal basis of T, P, R, n plus 1, which can be identified with R n plus 1. Now, how to construct a map which sends this basis into this basis? So let alpha be the matrix. Now, of course, here I am identifying the map with the matrix. This is clear. Whose columns are the elements of this basis. Since this is an orthonormal basis and P is length 1, then alpha belongs to O n plus 1, and it is clear that alpha dot, okay, let's say that alpha sends the basis delta 1 delta n plus 1 to B1, Bn, P hat by construction. And since in particular we have that this vector is sent to this vector here, it is clear that the image of the North Pole will be equal to P, and we can also say that the differential at n is a map from this tangent space to this tangent space, and it is represented by the same matrix, because we constructed alpha to be a linear map, and this says that the alpha n of delta I, this is beta bi for I equal 1 to n, and this says that alpha dot delta 1 delta 2 delta n, this is b1 b2 bn, that is alpha acts on this basis, sending it to this other basis. Now I want to use the example of the sphere to introduce the notion of conformal matrix and conformal diffeomorphisms. Suppose that G1, G2 are Riemannian matrix on a smooth manifold M, then G1, G2 are conformal or pointwise conformal or conformally related. There are three possible expressions you can use if there exists f in C infinity M positive such that G2 is given by F times G1. Now, what is a conformal diffeomorphism? Suppose that phi is a diffeomorphism between two Riemannian manifolds, so diffeomorphism. It is conformal if phi star g tilde is f g, where f is in infinity m, f strictly positive. Another expression you can use instead of conformal diffeomorphism is the following. You can say that phi is also a conformal transformation if such map phi exists. Then mg and m tilde g tilde are said to be conformally equivalent. The last definition I will give is the definition of locally conformally flat manifold. Mg is locally conformally flat if every point of M has a neighborhood that is conformally equivalent to an open set of Rn equipped with the Euclidean metric G bar. The reason why we use adjective locally, the adverb locally, is that we work with neighborhood. And the reason why we use the adjective flat is that we are in some sense comparing locally this manifold with Rn G bar. Now, why I said that I want to use the example of the sphere in order to present the notion of conformal map? The answer is the following. There exists a map sigma defined on SNR minus the North Pole and Rn, known as a stereographic projection from the North Pole which is a conformal diffeomorphism. Let's quickly review how to construct this map. I'm sure that all of you know it already. So suppose that this is S N R with n equal 2. I can make the picture only in this case. Then this will be the North Pole. And let's suppose that this is a point P of the sphere. Then the pseudo-graphic projection sends the point P to the intersection of the line joining N to P and the horizontal plane R2. This is the horizontal plane R2. So let's call this sigma P equal, I will call this U in R2. Let's introduce some notation. So suppose that P is coordinates C1, C2, Cn tau, and U equal U1, U2, UN 0. The reason why there is a 0 here is that this point can be seen as a point of R3 also, because of the ambient manifold is R3. And there is a 0 here because this is the set of points of coordinate C1, C2. Let's use the letter tau such that tau is 0. It's possible to prove that sigma of C tau, where C represents C1, Cn, it is given by Rc over R minus tau If you observe this formula, you get that this is U1, U2, UN. We want to prove that this is a conformal diffeomorphism. How to prove it is a diffeomorphism? Let's observe this map. This is defined on the entire sphere minus North Pole. So this is a smooth map. We have to find the inverse. It is possible to prove that sigma inverse of U, where U is U1, U2, UN, it is given by 2R square U over U square plus R square. R length of U square minus R square divided by length of U square plus R square. This map is clearly smooth, and this proves that sigma is a diffeomorphism. Now, how to prove that it is conformal? We will use a technique for computing the pullback of the Euclidean metric we used in the past. Precisely in the past, we have seen that if x from an open set U, so now I'm changing the notation, U is not this point, but this is an open set. If this is a parametrization, smooth, local parametrization, of a manifold M, then if M is equipped with if Rn is equipped with the Euclidean metric, what is the induced metric on U? This is the pullback of G bar, the Euclidean metric, by X, and we have seen that this can be written as sum of dxi square, where xi are the components of x. So x is given by x1, x2, xm. Let's observe that sigma inverse which is this map here, is a smooth parameterization of SNR minus N. Sigma inverse goes from R, let's say N, to Rn plus 1. So this plays the role of open set U, and in this case we have that M is N plus 1. So if we want to find the pullback of this pullback of GR, this was the symbol for the round metric of radius R. Then this is given by sigma inverse star G circle R. But what is a G circle R? G circle R is the restriction of the Euclidean metric to the sphere. So we can do this. And now I apply the formula I raised, and I get sum on J of differential of 2R square uj over length of u square plus R square plus differential of new length of u square minus R square, length of u square plus R square. So this is the ith component of this function here, and this one is exactly this function here. There are some computations to do. You will find the details in the textbook. And it's possible to find that this is equal to 4R4 length of u square plus R square square G bar. So we found that the pullback of this metric is given by the Euclidean metric multiplied by a strictly positive function. And this says that sigma is conformal It is immediate to prove that a sphere with the round metric is locally conformally flat. It follows from this formula essentially. Why? Because we can say that if P different from N, the North Pole, P in S and R, then S and R minus N, this can be seen as an open neighborhood of P, and we proved that there exists a conformal diffeomorphism between this open set and the Euclidean space. It remains to handle the case when P is equal to N. In this case, you can do two things. Or you use a rotation so that the North Pole is sent to another point, or you can use the stereographic projection from the South Pole, which is a more complicated thing to do. And in this case, you could prove that S and R minus the South Pole S, this is conformally equivalent to RNG bar. And it is done. Now let's talk about the hyperbolic spaces. Let's fix n greater or equal to 1 and r a positive real number, then h and r, this is what we call hyperbolic space of radius r. In order to provide you with the definition of this new manifold, I have to tell you what is a pseudo Riemannian metric on a smooth manifold M. This is a smooth symmetric two tensor. When we write this way, I mean covariant to zero tensor field G that is non-degenerate at each point of M. So the difference with the definition of Riemannian metric is that we don't impose G to be a positive definite inner product, but just non-degenerate. What does it mean to be non-degenerate? At each point of M, so GP is non-degenerate if one of the following equivalent conditions is satisfied. One, for every V in TPM, there exists W in TPM such that GP VW is non-zero. Two, the matrix GP IJ, this means the functions that you get if you write G in local coordinate is invertible. Then for non-negative integers Rs, the pseudo Euclidean space of signature RS, denoted by this symbol, is the manifold R plus S with coordinates C1, C2, CR, tau 1, tau S, and it is equipped with the pseudo Riemannian metric Q bar RS, given by the formula dc1 square plus dc2 square, r square, and minus, not plus, d tau 1 square minus d tau s square. If s is equal to 1, then this kind of metric are called Lorentzian or Lorentz metrics, and in the R1 is what we call R plus 1 dimensional Minkowski space. Now I'm ready to give you the definition of it's actually a theorem. The definition of hyperbolic space. So theorem, the following Riemannian manifolds are all mutually isometric. So what I'm going to do now is to give you a list of models of the same manifold. We call this manifold hyperbolic space. The first model is known as hyperboloid model. So it is the submanifold of Rn plus 1, Rn1, so we are using this notation here. It's a Minkowski space of dimension n plus 1, defined as the upper sheet tau positive. So I am using tau instead of tau 1. Do you remember our coordinates for this kind of spaces are xi1, xi2, xr, tau 1, tau s. In this case s is 1, and instead of writing tau 1 I will just use the notation tau. Of the two sheeted hyperboloid of equation C1 plus, C1 square plus C2 square plus Cn square minus tau square equal minus R square with the induced metric denoted by this symbol G'1R equal I star Q bar, where I is the inclusion and Q bar is the metric, the pseudo metric Q bar n comma 1 given by the C1 square plus the Cn square minus the tau square. Second model, Beltrami-Klein model, denoted by KNR, is the ball of radius R centered at the origin of Rn with the metric given in the coordinates W1, Wn by this long formula G-2R. This is R squared times dW1 squared plus dWn square over R square minus length of W square plus R square W1 dW1 Wn dWn squared divided by R squared minus W length of W squared. This model is not so useful in practice because of the more complicated formula for the metric. The two models which are, in my opinion, more useful from the computational point of view are the last two, that is the Poincaré Bow model, denoted by BNR. This is the bow of radius R centered at the origin with the metric in the coordinates U1, U2, Un given by G-3R equal to 4 R4 du1 square plus dun square divided by R square minus length of u square. The last model is known as Poincaré half-space model. It is denoted by UNR. This is the upper half space. In Rn, defined in the coordinates x1, x2, xn minus 1, y by un r equal to the set of points of coordinate x, y, where x represents x1, x2, xn minus 1, such that y is positive. I endow it with the metric G chess 4R is R square times tx1 square plus tx2 square plus dxn minus 1 square plus dy square divided by y square. I will prove this theorem next time, but I want to explain what we will do. We will construct some isometries between these models. Precisely, we will construct an isometry C from H and R and K and R. Pi between H and R and B and R. K between U and R and B and R. Some of you could make the following remark. We define this guy to be the upper sheet of an hyperboloid of Rn1. So the first step of the proof of the theorem is to show that the induced metric is not a pseudo-metric, but is a Riemannian metric. Because we want this to be a Riemannian manifold. Let's stop here. Thank you for your attention.